Greetings, physics friends. Welcome to AP Physics 1, Unit 2, Lesson 7, where the topic for today is Newton's third law. Newton's third law. So in order to understand Newton's third law, you have to understand a very simple vocabulary word, the word action. So in Newton's third law, and when we're talking about things Newton said, you need to understand that the word action is not an event. The word action is not an occurrence. The word action is and only is, 3 bars in an equal sign means it's a definition. Action means force. That's all it means. If you take away the word action and instead say force, you will not change the meaning at all. In fact, you will make the meaning clearer. So most people can say Newton's third law, even though they don't realize it, they can say it. And after they say it, they still have no idea what it means. Newton's third law is every action, you go, oh, I know. Yeah, every action has an equal and opposite reaction. Now, a lot of people think that that has to do with, oh, so if I stop and help someone change their tire, and then the next week when I forget my lunch money and someone gives me an extra quart, no, that is not a reaction. Every force comes with an equal and opposite other force. That's what it's saying. Still not very clear, is it? So we'll write it down. You can write it down too. Every action, and then we're going to cross out action and write force, because that's what Newton meant when he said force. Every force has an equal and opposite reaction. And then we're going to cross out action and write force. So there's two things about these two forces. There's the original force, and then there's this reforce. And there's an equality that's true about them, and there's an oppositeness about them. Sounds complicated. It is so not. So let's see what it says. Am I pushing down on this piece of paper right now? Yes. Dr. Platt pushes paper down. Oh my goodness, that sounds like the fourth sentence. Yes, and again, the fourth sentence is the answer to understanding physics. So we'll say, Davy pushes paper down. Pusher, then we say the word pushes, pushed direction. That's the fourth sentence. A pushes B that way. Davy pushes paper down. Newton's third law says if that's the action force, the reaction is paper pushes Davy up. The paper is pushing up on me. For the action force and the reaction force, all we do is take the pusher and make it the pushed. And we take the pushed and make it the pusher. But what about, there is no but what about, there is no, well, what if, there is no what if. That's what we're talking about. A pushes B that way, B pushes A the other way. So that's another way we could write it. I'll put it in another color. A pushes B that way, up and right. That means that B pushes A, same direction, but the opposite direction, down and left. So not really the same, opposite direction. If you use the force sentence, you will never get Newton's third law wrong. But if you do weird things, say like, oh, well, this object's weight, pusher, pushes, pushed. Now, Newton's third law, every force, every action has an equal and opposite reforce. So if this is the force, this is the reforce. If this is the action, this is the reaction. If this is the action, this is the reaction. If this is the action, this is the reaction. Just have to switch that order. Newton's third law says that they're in opposite directions, and Newton's third law says they're equal. So David pushes paper down, paper pushes David up. Who pushes harder? Nobody pushes harder because they're equal sized. Well, what if this other thing is also going on? Well, that doesn't matter. There is no what if. I'm going to pause for a sec. I pressed pause for a moment and I can't remember what it was I was saying. So I apologize if I repeat myself. But Newton's third law, every action has an equal and opposite reaction. All that means is that if you say the force sentence, this other sentence is also true, where you take these two nouns and switch their order. It is true for every force that exists in the universe. If A pushes B that way, it is also true, no matter what, it is also true that B pushes A in exactly the opposite direction. And the number of newtons that each of these forces is the same number of newtons, exactly. So if my fist pushes my cheek pushes my fist. Okie dokie, that's the way it always is, always. There is no exception. And so there's just a lot of misunderstanding about it, but there you go. You know, I joke about, and don't ever act this out, but, you know, I joke about two little siblings. And, you know, sibling A, you know, walks by sibling B and smacks the other one, you know, on the shoulder. And the sibling whose shoulder got smacked says, you know, Mom, you know, sibling hit me. And then the sibling could reply, well, that one hit me too. Hand hit shoulder, shoulder hit hand. Well, he hit me first. Oh, that's so funny. No, this cannot happen before this happens. They happen simultaneously. Well, he hit me harder. No, A pushes B with exactly the same number of newtons of force as B pushes A. That is Newton's third law. No more, no less. All right. So how does this relate to a free body diagram? What if I were to draw a table here with some blocks on it? What if I had a block here and it's being pulled by a rope, which is attached to another block, which is attached to a rope? And we'll call this T1 and we'll call this T2. And then I just set another block here. Now, for those of you who are looking ahead in the textbook, this is problem 27 in the back of your book. And then I'm just going to call this, this block has a mass M1, and this block has a mass M2, and this block has a mass M3. And I'm going to draw the three blocks down here. And I'm going to suggest that this would be a great activity for you. Can you draw the free body diagram of this block? Can you draw the free body diagram of this block? Can you draw the free body diagram of this block? Just a sec. I think if you do it right, I was just counting really quick, there should be a total of 11 forces. I'm going to write 11 question mark because I'm pretty sure there's 11, but I was counting in my head. So there's no friction. It's not a frictional table. It's a frictionless table. So no frictional forces. See if you can draw the three free body diagrams. Press pause and see how you do. All right, and we're back. So I'm going to start with this one and say Earth pulls it down with a force M3G. Why don't I just do the Earth force on all of them? Earth pulls this one down, And Earth pulls this one down, M1G. Makes sense, right? The Earth pulls each of the blocks down. All right, now who else pulls on block 3? Well, this rope pulls block 3 to the right. So I'm going to call that T1. And this rope pulls block M3 to the left. So I'm going to call that T2. And the table pushes block M3 up. So I'm going to call that a normal force, because when a flat planar surface pushes perpendicular, we call that a normal force. Does anybody else push block M3? Can you name, so, Earth pulls block down, string pulls block right, other string pulls block left, table pushes block up. Force sentence. There's nothing else. Now, let's go over here to block M1. Earth pulls the block down, the rope pulls the block to the right. I'm going to call that T2. This string is the same string as pulls this one to the left. If there were friction, I would draw a frictional force here. Table pushes this block to the left, but there's no friction. And then I'm going to say the table pushes this block up. Now that's a normal force. And this was also a normal force, but I don't know if the table's pushing this block up with the same number of newtons as it pushes this block up. So I'm going to call this Fn1 and this Fn3. The table pushes block 3 up. And so those are just two different normal forces. The table can push different things up with different numbers of newtons. And you might be feeling like that's all. There's actually one more force, but I'm going to put that on pause for now. Let's go to this block. Earth pulls this block down. The table pushes this block up. I'm going to call that Fn2. And then do you see that this block pushes this block to the right? That's how that happens. If I pull here, everybody moves to the right, and this block pushes this block to the right. So I'm going to call that F12. Block 1 pushes block 2 to the right. Block 1 pushes block 2 to the right. Does that make sense? That this block pushes this block to the right? I hope it does. Does anybody push this block to the left? No. But if block 1 pushes block 2 to the right, according to Newton's third law, if block 1 pushes block 2 to the right, then block 2 pushes block 1 to the left. Therefore, there's one more force here. Block 2 pushes block 1 to the left. Now, who pushes harder? This one or this one? Who pushes harder? That's right. Every force has an equal and opposite force. So this force and this force are the same number of newtons. So I'm also going to call this F12. So, and I don't have to call it, F21 or negative F12 because I've got the arrow on there. So I know that the block 1 pushes block 2 to the right and block 2 pushes block 1 to the left with the same number of newtons. So this is not two variables, this is one variable. And now let's see if I counted right, if 11 was the right number. 4, 5, 6, 7, 8, 9, 10, 11. Cool. So those are the forces involved in this setup. This is the force that people often forget to put on there. They forget that this block is pushing this block to the left. So then if I wanted to solve for something, I would write F equals MA. T1 minus T2 equals M3A. T1 minus T2 equals M3A. On this one, there's only one horizontal force. F12 equals M2A. And on this one, I've got two forces. T2 minus F12 equals M1A. 3 equations. And so some of these things would be given and others would not be given, and you could figure out the answer. I think usually they would give you T1. They'd say, how hard you pull. So T1 would not be a variable. And then what I'd be solving for would be probably T2 and F12 and A. They'd also give you the 3 masses. And I could solve 3 equations for 3 unknowns. We don't have to do that. I just want you to understand the setup. Action, reaction, pairs. So I hope that demonstrates for you how the force sentence clarifies these things. The final thing I want to say about Newton's third law here is notice that we said the table pushes block M3 up, and we drew this arrow. Does block M3 push the table down? Yes. This block pushes the table down. Did I draw a free body diagram of the table? No. So that's a force that acts on, that pushes the table. If I wanted to draw a free body diagram of the table, I could. But M3 pushing the table is not a force that goes on block 3. Only the forces acting on pushing block M3 go on here. So a good idea at this point is to say, can you say the force sentence for all 11 of these? Make sure you can. If you cannot, ask me when you see me. Additionally, if you had an additional force that I did not put here, then try creating the force sentence. Do you know who's doing the pushing and who's getting pushed? Ask me about that if you have a force sentence for a force that I did not include here. All right. Now, that was number 27 in the book. Now, what I'd like to do is, let's say that I have a stack of books sitting on a tabletop. So here's a table, and here's a book, and then here's another book, and then here's another book stacked on top. They can be books, they can be boxes, whatever. And let's say that I'm going to push here. P. Dr. Platt pushes this box to the right, and we go across the ground. And all the boxes move together. Let's say that we're on an ice skating rink, so we don't have to worry about friction here between this bottom box and the ice, or the bottom book and the ice. But there is going to be friction in here, and there is going to be friction in here. And we'll just call this mu sub S1 and mu sub S2. And if you know that, and we call this block has a mass, this block has a mass M1, mass M2, mass M3. Can you make 3 free body diagrams for me of these 3 blocks? That is a fun challenge. So again, press pause, see about putting M3, M2, M1, about putting forces on there. On your mark, get set, go. Okay, and welcome back. So we're pushing this block to the right, and we're moving to the right. So of course I have P here pushing to the right, and Earth is pulling the block down, M1G, and the table is pushing this block up. I'm going to call that FN1 because I am anticipating that there are going to be other normal forces. And do you see the block M2 is pushing block M1 down? Do you see it? If you don't, I'll make it more obvious later, but right now I'm going to call this, I'm going to call it F21. Block 2 pushes block 1 down. Now there's one more force here, but I'm going to leave it for a moment. If you know about it, that's great. Let's go to block 2 now. Who's pushing block 2? Well, of course, Earth pulls block 2 down, M2G. And who pushes block M2 up? Who pushes block M2 up? Block M1 pushes block M2 up. Now that's a normal force. I could call it N2. But do you also see that that is the reaction force of this? Block M2 pushes block M1 down, block M1 pushes block M2 up. Remember our force sentence relationship. A pushes B one way, B pushes A the other way. So if this block pushes this block down, and I call that F21, then this block pushes this block up, that's F21 as well. F21. Those are normal forces. Sometimes I call those the squishingness forces. It's how hard the two blocks are pushing each other together. That squishingness will matter in a minute. And so vertically, let's see, this one pushes this one up. Earth pulls this one down. Ooh, this one pushes this one down as well, doesn't it? M3 pushes M2 down. So that's F32. Any other vertical forces on M2? I don't see any, right? Do you? All right. Now, this block, when I push here and I push them all to the right, who pushes this block to the right? This block pushes this block to the right. That's how it goes to the right. And so I'm going to call that a frictional force. M1 pushes M2 to the right. That's a frictional force. All right. Now, I told you there was one more force here. If this block pushes this block to the right, then this block pushes this block to the left. Action, reaction. And that's going to matter in terms of our equations. Now let's go up to this one. Who pushes block M3? Earth pulls block M3 down. And M2 pushes M3 up. That could be, FN3, but I'm going to call it F32. Because this is top block pushes middle block down, middle block pushes top block up. Those two should be the same number of newtons. This block also moves to the right. Who pushes it right? This does. So that's also a frictional force. I'm going to call that FF2. So now I have to take these frictions and make them FF1. Middle block pushes top block right. If middle pushes top right, top pushes middle left. F2. So what often happens when people are making these free body diagrams is they put one of the forces, but they forget to put the reaction force. They put a force, they forget to put the reaction force. And if you forget to put the reaction force, you're going to get the problem wrong. So here's what I want to do now. We could do 1, 2, 3, 4, 5, 6. We could write F equals MA 6 times, horizontally and vertically, horizontally and vertically, horizontally and vertically. I just want to focus on this one. And I want to write sigma Fx equals M2A and sigma Fy equals M2A. What are the horizontal forces? Frictional force 1 minus frictional force 2 equals M2A. Vertically, I've got this arrow, oh my goodness, that I didn't label. Who's pushing this block up? M1 pushes M2 up, which is the reaction of M2 pushes M1 down, F21. Oh, I already drew that there. Maybe that was the problem. I don't want to have the same force on there twice. Thank goodness I knew how to label it. Who's pushing this block up? Just the bottom block pushes this block up, and I've already got it there. F21 minus F32 minus M2G equals M2A. So that's how I would write those equations. Now, I told you once there's a frictional force in an equation, on the next line, you replace the frictional force with mu times the normal force. The normal force, there's a lot of normal forces, and actually there's 2 mu's. So how do I determine which mu's? FF1, this one, is bottom block pushes middle block to the right. So if bottom block is pushing middle block to the right, that should have to do with this contact. So the mu is mu S1 times the normal force. It's how hard these 2 blocks are being squished together, F21, minus FF2. This force is top block pushes middle block left. So that has to do with this interface. So it's mu S2 times how hard these 2 are being squished together. And that's F32, these 2 being squished together. Now that might be one of your challenging moments. Again, figuring out which mu to use and which normal force to use. You could do something similar for this free body diagram, these 2 equations, and something similar for this free body diagram, 2 horizontal and vertical F equals ma equations. And that would give you 6 equations that you could solve for 6 unknowns. It's not as hard as it seems. And again, you don't have any of the numbers here, so you couldn't do this. I'm just setting up something kind of complicated, hopefully to give you the right things to think about. All right, that is Newton's 3rd law. There's a lot going on in this video. I would suggest watching it more than once. Have a great day.